Hi folks, today we have a new topic and it's called similar polygons. So we just finished talking about transformations, and most of the transformations that we discussed were isometries, meaning that the pre-image and the image were congruent to each other, same size, same shape. Now today when we discuss similar polygons, we're discussing figures that are similar, meaning they have the same shape, but not necessarily the same size. So that's what's different about this. And whenever you talk about similar things in everyday conversations, you're talking about things that are kind of the same. Well, that's what similar means here. It's just more specific in geometry. Similarity implies the same shape, but not necessarily the same size. So we have an example. We have triangles 1 and 2. Triangle 1 is similar to triangle 2, and here's the symbolic representation of that sentence. I know they're similar because they're the same shape and they're not necessarily the same size. Now in this example, this pair of triangles are not similar to each other. Now while they're both triangles, they're not the same shape triangle, and so these are not similar to each other. And here's the symbolic representation for that. Now, we say that two polygons are similar if and only if, so there's that biconditional phrasing, if and only if the corresponding angles are congruent and the corresponding sides are proportional. So we discussed proportional a few days ago, but we need those two things to happen in order to prove that polygons are similar. We need them to have corresponding angles congruent, and then we need corresponding sides proportional. So let's talk about the corresponding angles. We have angle A, and we have angle X. And angles A and X both have one arc mark here, so we can say that angle A is congruent to angle X. Now let's talk about angle B. Angle B has two arc marks. Angle Y has two arc marks. Angle B is congruent to angle Y. Looking good. Last pair, we have angle C with three arc marks, angle Z with three arc marks, so angle C must be congruent to angle Z. So we've satisfied the first condition in order for these triangles to be similar to each other. Now the second condition implies that the corresponding sides must be proportional, meaning if I create a ratio of corresponding sides, maybe big side to small side or small side to big side, and I maintain that ratio throughout, and I try to figure out what all three ratios are, if they're all the same, well that means that my sides are proportional. So let's create ratios of, we'll say, smaller side over larger side. So we're going to pick a side from the smaller triangle and we're going to put it over the corresponding side of the larger triangle. So let's talk about XY. XY's corresponding side goes from an angle with one arc mark to two arc marks. So from 1 to 2, that would be side AB. Well, side XY's length is 5. Side AB's length is 10. And 5 divided by 10 can be simplified to 1/2. So let's do the same thing with the other sides. So let's go ahead and talk about side XZ. Goes from 1 to 3 arc marks, and 1 to 3 arc marks is side AC. So those are my corresponding sides. XZ has a length of 6. AC has a length of 12, and 6 over 12 can be simplified also to 1/2. So why don't you pause your video and try to find the last ratio and see if it matches. Now hopefully your work matches mine. I do want to point something out though, that remember whenever you're creating these ratios, you need to have kind of like the same key going on. So if the smaller triangle is giving you your numerators, then your larger triangle needs to be giving you your denominators in every single ratio. So that way you can compare. Now I notice that all of these are 1/2, which is good because that's what it means to be proportional. That means that if I create ratios of all the sides, then whenever I simplify them, I'm going to get the same number for every simplified ratio. So on the next page, let's identify the pairs of congruent angles and corresponding sides, and let's see if we can determine if these two triangles are similar to each other or not. So I notice the first thing in my pair of triangles is that they're right triangles. So that means the angles B and G are congruent to each other because they're both 90 degrees. In this triangle, I have angle C at 59 degrees. And here I have angle H at 59 degrees. So angle C and H must be corresponding because they're congruent to each other. Now, if I know that these two angles are congruent to these two angles, then what do I know about the third pair of angles between the two? Well, I know that that third pair, angle A and angle J, must be congruent to each other, and that's by the third angle theorem. So the first component of being similar is satisfied, that my corresponding angles are congruent to each other. Now all I have to do is to determine if the corresponding sides are proportional. So I already have one ratio that's kind of laid out for me. Side AB comes from the larger triangle, and side JG comes from the smaller triangle. So I'm going to have large number over small number in all of my ratios. AB has a length of 10, JG has a length of 5. So 10 over 5 simplifies to 2. Now I need to find another ratio, and I'm going to go from large side to small side. So let's go ahead and take the hypotenuse of the large side, AC. That's 11.6. And the hypotenuse of the small triangle is HJ. That's 5.8. And when I divide 11.6 by 5.8, I end up with 2 again. So I want you to pause your video, create the key for the final ratio, create the final ratio, and simplify the final ratio, and make a conclusion about whether these two triangles are similar or not similar. Pause your video. So check your ratio with my ratio. Keep in mind that in the first ratio that was provided for us, AB was from the large triangle, so we need to make sure that the numerator is from the large triangle each time. So all of these come from the large triangle, and all of the denominators come from the smaller triangle. So that looks right. All of my ratios are 2, and so if they're all 2, that means that the corresponding sides are all proportional to each other, and these two triangles are similar. So I can say that triangle ABC is similar to triangle, and I need to get the order right. Angle A is congruent to angle J. Angle B is congruent to angle G. And angle C is congruent to angle H. So there's my conclusion. Now, what we've been finding whenever we try to determine proportionality of corresponding sides is we've been finding a similarity ratio. Aptly named because we're finding the ratio and determining if two things are similar. So a similarity ratio is the ratio of lengths of the corresponding sides of two similar polygons. So I want you to recall something from a few sets of notes ago. So I want you to recall that ratio can be written in a few different ways. So it can be written as like a value x to a value y. It could be written as x colon y. And it can also be written as x over y. And this is the way that we're typically going to write it, but you don't always see it that way. So in a similarity ratio, you have to be prepared to identify the first and the second figure and keep them in that order. So the similarity ratio of triangle ABC, the small one, to triangle DEF, the large one, has to be the small number first and the large number second. So small to large, small to large. So my similarity ratio, I can just go ahead and find one ratio for corresponding sides. So the small triangle has a side length of 3. The large triangle has a side length of 6. And 3 over 6 is 1/2. So there's my similarity ratio from triangle ABC to triangle DEF. Now this bottom one is really closely related. It wants the similarity ratio, but this time it wants the ratio from triangle DEF to triangle ABC. So it wants from large to small. So you need to invert your numbers. So from the large triangle, a side length is 6. Its corresponding side is 3. And 6 over 3 is 2. So notice how the similarity ratio isn't necessarily one right answer only. It can have 2, but you have to pay attention to the order. So if we're going from small to large, this is the similarity ratio. If we're going from large to small, this is the similarity ratio. So let's move to our last page of notes. So the last page of notes, we've got 2 examples here. The first one says, is triangle MLJ similar, remember this means similar, to triangle NPS? If so, write the similarity ratio and a similarity statement. So we need to provide the ratio and we need to provide the similarity statement. So I'd like for you to pause your video. I'd like for you to identify whether or not these 2 triangles are similar. Remember, you have to make sure that the corresponding angles are congruent and the corresponding sides are proportional. So take a moment to pause your video and try this problem. Check back for the answer. Okay, so we've been able to see that we have 2 pairs of corresponding angles that are congruent. The third pair must be congruent by the third angle theorem. We have a ratio already set out with a large triangle value over a small triangle value. So if you continue with that pattern for the ratio, you end up with 5/2 as the ratio for each pair of corresponding sides. So because we have all 3 corresponding angles congruent to their other angles, and we have all 3 corresponding sides proportional, then we can say that yes, these 2 triangles are similar. So here's the similarity statement that's actually already given to you at the top. And the similarity ratio from triangle MLJ to triangle NPS, large triangle to small triangle, is 5/2. So let's move this up to the last example. The last example says that rectangle DEFG is similar to rectangle HJKL. And it wants to know what is the length of HJ. Well, if we're talking about rectangles, we know that all of the angles must be right angles, so that kind of helps us understand that these 2 rectangles really should be similar. And then finally, we know that the corresponding sides must be proportional. So I need to create a proportion with my sides and my missing side HJ. So this is going to be my missing side HJ. I don't know what this is. If these are rectangles, then that means that 27 inches here will be 27 inches here. 40 inches, 40 inches. So short side, long side, short side, long side. 18 inches, 18 inches. X inches, X inches. So if I create a proportion, perhaps I create a proportion with a large value on top and the small value on bottom. A large value on top would be 40. That's the long side of the large rectangle. And the long side of the small rectangle is X. That's our unknown value. Again, from the large triangle, we've got a side of 27 inches. That was the shorter side. And the shorter side in the smaller triangle is 18 inches. So now you have a very intermediate school problem that you can solve. So if you're trying to determine if these two are similar, you can cross multiply. 27 times x is 27x. 40 times 18. Now if you want to go ahead and do that multiplication and division, you're welcome to, but I noticed that 27 and 9 are both divisible, or sorry, 27 and 18 are both divisible by 9. So I'm going to go ahead and divide by 9 and get some smaller, easier numbers to work with. So 40 times 2, that looks much nicer. So 3x equals 80. And if I divide by 3, my side x, which is the side HJ length that I'm looking for, is 80 over 3. And I give it its units. We're measuring in inches. All found because we know that these two figures are similar, meaning that their corresponding sides must be proportional.